Okay, so good evening everyone. I am Aryan Mehra from Physics by Aryan. Okay, so today we are beginning the quantum mechanics in 3 dimensions. Now, the first question comes that why to study this topic? Number one is it is a foundation of quantum mechanics for MSc. Okay, in BSc, whatever quantum mechanics you have studied, it does not include quantum mechanics in 3 dimensions. But now in MSc, this is a very foundation topic of quantum mechanics. It is not possible that question does not comes from this topic in GATE, NET, JEST, TIFR. In all the exams, it is almost sure that question is going to come from this topic. So that is why I am making these 4 or 5 lectures on quantum mechanics in 3 dimensions, because otherwise it is very hard to understand by yourself by reading the book. But since this topic is not that hard if someone teaches you, so that is the reason I am taking these lectures. So I would recommend you to stay regular. There will be 4 lectures. Number 1 lecture today we are taking is about the basic knowledge about the states. What are quantum states? What are eigenstates? Okay, what are the eigenvalues and what are the operators? And how, if I give you some operator, how you can write the metrics for that operator. Okay, what is operator and so on. If you don't know, don't worry, I'm going to explain today. So this will bring entire BSc quantum mechanics which you need. I will summarize today and also teach you how to do the matrix formulation, so that you can shift towards the quantum mechanics in 3 dimension. So let's just begin. Okay, so number one idea which you need to understand about is what are the states in quantum mechanics. Okay, so it's a very trivial question, but you have to understand it very nicely. For example, in classical mechanics, what happens? We know classical mechanics. We always compare classical mechanics with quantum mechanics in order to have a better physical understanding. Because no one can imagine quantum world, but everyone can imagine classical world. What happens in classical mechanics? Ball is moving with some speed, velocity v. These kind of questions we are solving from class 11, 12th when we first studied the physics. So ball is moving with velocity v in one direction. What we do? It experiences some force F, let's say gravity, force F. Okay, and then we have a one very fundamental equation in classical mechanics. Can anyone name that equation? What is the most fundamental equation in classical mechanics? Very quickly, if you can name.
F equals to ma.
Yes, F equals to ma. Yeah, so F equals to ma is a Newton's second law equation which you should know. So we write a Newton's laws equation, then we solve this equation, we get an acceleration. From acceleration, what we get? We get a velocity. From velocity, we get a position. Similarly, you can find this force formula to find the work done, to find the energy. Everything you can know if you know the solution of this equation. Very simple is that. Okay. Now what happens in quantum mechanics? Well, now let's first discuss what is state in classical mechanics. State. So how do you describe the state of this particle which is moving? We say, okay, this particle is moving with velocity v, so its state is described by 2 things. One, its position. What is its position? And let's say what is its momentum. So it is a one way of describing the state. Why only this? Because if we know x, we can know velocity, we can know acceleration, and if we know momentum, we can find work done and we can find energy. So this is a one way, that what is its position at all the times and what is its momentum at all the times. This is called the state. State means some information about the system. Okay, everything clear till now? Very simple. What happens in quantum mechanics? In quantum mechanics, we are also interested in state. What do I mean by state? So I always start explaining the state from a very simple example of electron. Always remember this example. Okay, electron. Now this everyone knows. Why everyone knows about electron? Electron has a spin. What does a spin of an electron means? It's very important. If you going towards the quantum mechanics in 3D, we always start talking about angular momentums. Okay, electron has a spin. Can anyone tell me what does it mean? Electron has a spin. Anyone, very quickly, what does it mean? Electron has a spin.
So it's an intrinsic property of an electron which has been observed by the Stern-Gerlach experiment. So we defined spin.
Okay, yes, okay. Anyone else want to go ahead? Let
It
it be
means that
interactive.
it appears to have different phases, but it does.
Okay. Okay. Very close to the right answer. Okay. So what does it means by electron having a spin? It does not means electron is rotating about some axis. Number one, it does not means that. Okay. Remove this from your brain. Doesn't means this. That there is an electron which is a sphere and it is moving around an axis. Just like an earth. It's not like an earth. Electron is not like an earth. What does spin of an electron means? So spin of an electron means that electron has some angular momentum. For example, electron has some mass. Okay. Mass. Okay. And electron has some angular momentum. Now, in classical world, whenever we imagine angular momentum, we assume something rotating. But in quantum mechanics, first rule is whenever you heard the word angular momentum ever in your life, never assume that it is somewhere rotating. Never assume. It may be rotating. It's not always true that it is not rotating. Sometimes it actually rotates, but not always. Then from where this angular momentum is coming? So it is the same question like if I ask you from where the mass is coming. Can you answer from where the mass of an electron is coming? Can anyone answer this? Yes, no. Very quick. Can you answer? Anyone answer? Yes or no?
No, it's again an intrinsic property.
Okay, so we can't answer how from where mass is coming. Everyone okay with that? Or anyone think you can answer that? If a baby is born, is it safe to assume that a baby will have a mass? Batao bhai.
Yes.
Yes, no. Is it safe to assume that baby will have a mass? Yes.
Yes, sir.
Yes.
So it is similar to that. If an electron is born, whenever an electron is born, it bonds with some sort of angular momentum, which we call it as spin angular momentum. Now there is a very specific reason to name it a spin angular momentum. Why don't we call it any random angular momentum? Why don't we call it intrinsic angular spin angular momentum? We will come it to the end of the fourth lecture. Why we call it as a spin angular momentum only. But why we assume that this is an angular momentum? Because electron had three features in it. Number one, it is had some mass. Had some mass means when we observed the electron, it started behaving like it has some sort of mass. Okay, it started behaving like it has mass. For example, if you measure the trajectory of an electron, for example, E by M ratio, when we measured, you came to some E by M ratio. That is why we can say that mass is there. It had some charge. From where it came, we don't know. It has some charge. And number three, it has intrinsic spin angular momentum. These three quantities it has. That is why we call it as electron has a spin. Very simple idea as that. We don't answer the questions like why it has spin, why it has mass, or why it has charge. It is a question, very fundamental question where we don't go. Then comes the next step. If it has a spin angular momentum, maybe in lower classes you have studied about one more parameter which we call it as ms and small s. Okay, these two parameters which you must have heard. Whenever we go to quantum mechanics, number one thing that comes into picture is called quantum numbers. Quantum numbers. Why it comes into picture, I will explain by the end of this lecture. Quantum numbers. These are the two quantum numbers which are required to describe the spin of the electron. What is S? S describes what will be the magnitude of this angular momentum. Electron has an angular momentum as vector. Now, since this is a vector, one thing is what is its magnitude, and second thing is what is its direction. So this small s is required to know what is the magnitude of this angular momentum, and this ms is required to know what is the direction of this angular momentum. How? This will be discussed in the third lecture, that how these two quantum numbers actually tell us the direction and magnitude of this spin angular momentum. For now, I want just to know that I just want to recap a class 11, 12th analogy so that you can understand what is the state of a system. Okay, so we know the spin of the electron is half. Just remember this. I am not asking you to think from where s equals to half came. I will explain that in third lecture, but for now we know the spin of an electron is half and ms is plus and minus half. What does it means? The electron can either be an up or a down. What does this actually up and down means? That is also will be discussed in detail in lecture 3rd. But for now, just remember that, just recap that we have heard from our birth, from our, not birth, from class 10th, 11th, 12th, that electron can take two positions, either up or down. Okay. So these are the two things you should recap. So this up and down is called the state. Okay, either electron is in up state or it is in down state. So the state is something, always remember, please write this definition. What is state? Something which gives an information, about some physical parameter of your system. So if I say that your electron is in state up, it means it is pointing, its angular momentum is pointing up. And if I say if it is in state down, it means it is pointing down. Okay, let's take another example to understand the state, which we call it as hydrogen atom. In hydrogen atom, what are the quantum numbers that you studied in class 11? Can you all name that? What were the quantum numbers that you studied? Yeah. Number one quantum number was
N, principal quantum.
Yes, N. And what else?
Azimuthal quantum number.
Yeah, that is L. L. And other than that, N, L, or
Magnetic quantum.
magnetic. So ML, MS. Do you studied MS? No, we don't study MS.
Spin quantum number.
ML. Spin. Okay, so basically there are many, but these three are good enough. So these three states we know. Okay. Now what does these quantum numbers again give you an information? What state you want to know? So if I tell you energy of the system, that it is the energy of your hydrogen atom is minus 13.6 electron volts. If I just give you this information, in which state your electron is, can you tell me that?
Ground state.
Ground. So what we say, it's a ground state. Okay, it's a ground state. Now ground state itself does not have any meaning. You give it a meaning in terms of something, some physical parameters. Read the definition again. Something, state is something which gives you an information about some physical parameter. What is a physical parameter here, which I defined? Energy. I gave you an energy. Yeah, I gave you an energy, and then you told me what it is in ground state. Another way of doing the same thing is you define a general thing, that your energy is minus 13.6 electron volts, divided by n square. N square. Am I right? Have you all read this formula very well in class, smaller classes? So
Yes.
your n gives you information about energy, and from that you can tell it is in n equals to 1 state, n equals to 2 state, n equals to 4 state, and so. But remember, do you in reality measure n? If I give you hydrogen atom sample, can you measure n? Can you measure n directly?
No.
No, you always measure energy. You always measure energy. So from energy, you know is it is n equals to 1 or 2 or 3 or 4. So what is state? State is something which gives you an information about some physical parameter. Now let's say you only measured energy and you know it is in n equals to 1. Can you also now tell me what is the velocity? Because you can, what is the radius? Can you tell me these two things also? Can you
Yes,
tell
sir,
me?
yeah, because formula,
Yeah.
formula.
Yes, it's yes, very simple, because for velocity and radius also we have the formula. So once we know that it is in n equals to 1, we know what is the radius of r, what is r1, and we also know what is v1. So we don't have to measure each and everything. We only have to measure one thing, and other things can be known accordingly. For example, in classical mechanics, if you know acceleration, if you measure acceleration, do you separately need to measure velocity, or can you just integrate it? You can just simply integrate the form and you get, and again if you integrated you get position. Now if you know force, you just integrate f dot dx and you get the work done. If you know the momentum, you just do p square by 2m and you get kinetic energy. So you measure 1 or 2 or 3 parameters which gives you all the information about the system. If you measure these parameters, all other information also comes into picture. So n is giving us the information about the energy. Now why we use L in hydrogen atom? Can anyone tell me? Wasn't n enough? What does the L gives you?
Sir, because the electron is revolving around the nucleus, so it has some angular momentum. So therefore, we have to define an orbital angular momentum.
So half of your thing right is idea is right, half of it is wrong. Can anyone tell me what part of it is right? Why we need L? Why we need L? Very simple, class basic smaller classes level question. What does L tells you in quantum mechanics in hydrogen atom?
Sir, another state of electron.
Another state. N equals to 1 is first state, n equals to 2 is second state. I have written it wrong. It's n equals to 1, it's n equal to 2. Okay,
Just because
it's
of fine
another
structure
state.
of hydrogen atom.
Fine structure and again come later. If I say n gives you energy, radius, velocity, then what does L gives you? What physical parameter it gives you? It's very simple. She has already named that parameter. Yes.
So the magnetization of the atom itself,
No. It simply gives you angular momentum, na?
angular
It
momentum.
simply gives you. Yeah. But which angular momentum? Orbital angular momentum.
The angular momentum of the electron.
Orbit.
Yeah. So Shraddha said something which is again half right, half wrong. Why? Let me go. Orbital angular momentum. But Shraddha said of electron. We don't know angular momentum of electron. Orbital angular. We always know orbital angular momentum of atom. We never say it's an orbital angular momentum of electron. Now, second thing which Sahin has said wrong is electron is orbiting around the nucleus, so that's why it has angular momentum. Again, I want you to rethink from the very basic classes. We have been taught in terms of Bohr model. Here, if you see, it's a diagram of Bohr model. But in quantum mechanics, Bohr model does not work very well. It works well in atomic physics. It does not work very well in quantum mechanics. So this is wrong. This diagram is wrong. This is a wrong picture of hydrogen atom. No electron is revolving around nucleus. In reality, no electron is revolving around nucleus. What it is doing, we don't know exactly, but it is behaving like it is revolving. In actuality, it is not revolving, but its behavior is similar like it is revolving. That's why we can say that we can just model it like it is revolving, but in reality it is not revolving. For we can tell that okay, why electron has a mass, because when it hits me, why something has a mass? Because when it hits me, I feel the pain. It means some mass has struck me. So we say it has mass. So similarly, it is a situation right here. We can't say electron is revolving. Atom and electron combined have some sort of angular momentum, which we call it as orbital angular momentum. In order to imagine, you can assume that electron is revolving around the nucleus. You can assume, but it's not a reality. Just to understand, you can assume. So to know this orbital angular momentum thing, we needed this quantum number. Now, can anyone give me a formula between angular momentum and, for example, like this formula? Very simple formula, direct formula. Can anyone give me a formula for magnitude of an angular momentum and this small quantum number L?
Sir, L
Very
into L
simple.
plus 1 extra square.
Root
L
over
into
L
L
into L
plus
plus
1.
1.
Yeah, this. Everyone agree with me this formula? If you don't agree, in third lecture, I will discuss more about this formula. But this formula, maybe you have heard somewhere. If you haven't heard somewhere, then heard it for first time. Now take it as a first time. This is a formula. Just like this is a formula that you are familiar with, minus 13.6 divided by n square. If you know n, you can know energy, also velocity and also radius. So if you know small l, you can know the orbital angular momentum. Very simple as that. Okay. So very first thing which I want to describe here in this formula itself. This formula itself is so beautiful. We can talk about it for hours because it's so important for our competitive exams. So from what is the number one thing which I want to discuss in this formula? What is the dimension of this quantity? Not h cut, but this quantity. L into L plus 1 under root.
Dimension.
Yes. What will be its dimension?
It's dimensionless.
Yes. How many of you say it's dimensionless? Say yes, no. Who says it's dimensionless? It's dimensionless.
Yes,
Okay.
sir. Dimensionless.
Because every quantum number is dimensionless. As far as I know, as per my knowledge, if there is some new quantum numbers discovered in last 10-15 years, I don't know about that. But all the old quantum numbers which we all know are dimensionless. So what does it tell you about the dimensions of h cut?
Sir, joule second. Energy into time.
No, it will have a dimensions of angular
Joules.
momentum itself.
Yes, sir. Yes, sir.
No, because if it is dimensionless, then it has a dimensions of angular momentum. Very simple as that. Okay. So this is what we want to say. Now I want you to connect it with the Bohr's model. What was the one postulate of the Bohr model which was very important? Can you give me a postulate of Bohr model?
Sir, the electrons revolve in such orbits for
Postulate
which the angular momentum is an integral multiple of h by 2 pi.
means it tells us that angular momentum's magnitude is a some integral multiple of h cut. So is it satisfied here from this formula? This will take some integer values, है ना? And it is multiple of h cut. So quantum mechanics and Bohr model work well with each other. You all know Bohr model,
Yes,
and
sir.
I am teaching you quantum mechanics. Are you able to connect both?
Yes, sir. Yes.
In lower classes, we only read the formula that angular momentum, which is mvr equals to nh cut. This formula everyone read. If you haven't read, then it means you have not done BSc very well. If all of you have studied this formula, it means an angular momentum is an integral multiple of h cut. And here also, it's almost the same thing. It is an integral multiple of h cut, because this value is dimensionless and it will take some integer values. Okay. This is something which you should know. Remember that h cut has a dimensions of angular momentum. So till here we have got a very good information about the quantum mechanical states. So what is the first information that we got? Whatever physical quantities which we can measure, then we connect those things with the states. So if we say we have energy E1, then it means it has state N1. If it has energy E2, it has state N2. If it has energy E7, it has state N7. Okay. Similarly, if it has angular momentum L2, it has state L1. Okay. And so on and so forth. We define a state of our quantum mechanical system with some physical parameters. That's a very simple definition. Now, moving to second thing. Physical parameters are actually a very, very important term here. So second thing to remember or learn about is physical quantities, or we call them as observables. Observables.
Excuse me, sir.
Yeah.
तो वो
Yeah, go ahead.
स्पिन एंगुलर मोमेंटम का समझ नहीं आ रहा कि वो अगर स्पिन उसकी इंट्रिंसिक प्रॉपर्टी है तो उसका एंगुलर मोमेंटम तो ऑब्वियसली फिर वो थोड़ा इंट्रिंसिक होगा, बिकॉज़ रोटेट तो करेगा ही ना वो.
No, this is a wrong analogy, na. Why you think if something has an angular momentum, it must be rotating? Why you think that? There must be some background thinking with that. Why you think angular?
Because angular momentum relates with the rotation.
Yeah, it usually in classical mechanics. And what I'm saying is now in quantum mechanics, many things are such like which will blow your mind. And this is one of that thing. Angular momentum has nothing to do with actually rotation. Why then we named it as angular momentum is something because if you try to build an analogy with classical mechanics, we can think maybe electron is rotating. Okay, we can assume it as rotating only to convince ourselves, only to imagine something. It is not actually rotating. Okay, electron has a charge. How you know that electron has a charge? Because it experiences a electric force. Am I right?
Yes, sir.
So you don't measure the charge directly, na? You measure the electrical force. Means electron is not touching another electron, but they both are repelling each other. Then we gave a very, very pseudo force, which we don't know at all. We say electric field. First time someone said electric field. They are not even touching. Okay. Till then, force was exerted only when both things collide. When both things collide, what happens? Mass. When both things collide and they exert force on each other, it tells you about the mass. Then another genius came. He says even without touching they are experiencing force. Then another intrinsic property came which is called charge. And then more things started happening because electron now not even with electric field but also start interacting with magnetic field. You understand my point? Now it is not only interacting with electric field but also interacting with magnetic field. From there another intrinsic property came out which is called angular momentum. So now you understand how the story is going.
तो मतलब कि हम एक्चुअली ये नहीं बोल सकते कि एंगुलर मोमेंटम में वो रोटेट ही कर रहा है, लेकिन कुछ फिनोमिना को एक्सप्लेन करने के लिए हम ये मानते हैं कि ये रोटेट कर रहा है ना, यही है.
नहीं हम मानते नहीं है. We don't accept that. we say that we can model it. Okay, we
सर
can
पर
model.
जैसे हमने स्पेक्ट्रोस्कोपी में नहीं वेक्टर मॉडल पढ़ते हैं तो उसमें प्रिसिजन का कंसेप्ट देखते हैं, तो वो उसमें देखते नहीं है कि वो हमारा जो स्पिन एंगुलर मोमेंटम है वो भी प्रोसेस कर रहा है, ऑर्बिटल एंगुलर मोमेंटम है वो भी प्रोसेस कर रहा है। तो
yeah, very good question, actually very good question. वो that is right, very precision. I am not saying that angular momentum not always means it is not rotating. In quantum mechanics also rotation will always bring angular momentum, but without rotation also we can bring angular momentum. How? For example, when an electron is rotating, it is assumed that, means why we say it's an angular momentum, because electron is interacting with the magnetic field. Because of this reason only we say it behaves like it has an angular momentum. That's the only reason. There is no proof of rotation. That's the only reason, because it interacts with magnetic field. That's why we call it as. And you wait for fourth lecture when we will discuss actually Stern-Gerlach experiment. Then you will have a better understanding why I'm saying that it has nothing to do with rotation. Okay. So now let's move to physical quantities, which we call it as observable. Yeah. Yes.
It is also applicable for spin or.
Yeah. Huh? Yes.
It is also spin.
Yeah. Spin. What does the spin mean? Spin means that electron has a spin angular momentum. Okay. Which we write it in terms of the spin quantum number. It has spin angular momentum, which we write it in terms of spin quantum number, and this quantum, ms quantum, magnetic spin quantum number. So that spin word is coming from there. Okay, that spin word is coming. Spin itself
Means
is nothing.
Electron is spinning, but not or.
No, I'm not saying electron is spinning. Please don't assume that electron is spinning. Electron has some intrinsic angular momentum, just like it has some mass. Spin word is only given so that you can imagine something about electron, nothing else. Yes, anyone? Yeah, someone was asking something.
Yeah.
Yes.
I want to say something, so please correct me if I'm wrong anywhere. It's like electron is not really revolving, but because of its interaction with magnetic field, it appears to have an angular momentum. And because 100%. Of that, we define that interaction as spin. Is it correct?
Yes, 100%. You have summarized it very nicely. It's exactly what is happening. Okay, because whenever science develops and science becomes a very important part, then we have to give a definitions in terms of what we already know. In defining that, all the confusion has been arise. Okay, now in relativity, if you go, then mass is something very confusing term. What is mass? You can't define in relativity. Do you agree with me? Can you define mass very accurately in relativity? Sometimes it's mass, sometimes the same mass is energy. Okay, so it's beyond that. We are just modeling it like it has spin, but it has no spin. Means it's not rotating, it has only angular momentum because it's interacting with magnetic field. Yeah, so let's move to observables now. In quantum mechanics, if you know two things very well, then your work is done. Number one, the state of your system. Number two, physical quantities. Okay, physical quantities which you can measure on that system. Okay, so for example, you have a hydrogen atom. So what are the quantities which you can measure? Number one, we can measure energy. We can measure, let's say, velocity, radius, angular momentum. Anything else that comes to your mind other than these? Anything? Energy, velocity, radius, angular momentum. So these are the basically the things which we measure for some different experiment. Now let's come to quantum mechanics. let's say you have a particle in a box. I assume that all of you at least know what is particle in a box. Potential is 0 inside and infinity outside, and the particle is somewhere inside. Not particle, quantum thing. I would say quantum thing is inside this well. What are the things that you want to measure for this? What are the
Energy,
things you
sir.
measure? Energy or position, momentum, position. Here you don't usually talk about angular momentum because intrinsically it does not have any angular momentum. If it is electron, then you talk. If it is not a spinless particle, then you don't talk about it. Okay, so these are the things you measure. So these all are called observables, quantum observables. Now, if you know this much, now let's move to the how we actually deal. Now this was actually what is the real, how I said, okay, measure the energy, measure the velocity, measure the, let's say you are a theoretical physicist for now. I am an experimental, but now let's assume you are a theoretical physicist. Now we will talk about, we won't measure anything. We will do everything mathematically. So what is state now and what is observable now? Now tell me what is state and observable. So now let's describe that. So state, observable is represented by a thing called operator. Is represented by operator. Okay. So mathematically, if you want to see what will happen, you do not all the time measure. Okay, if I give you, you throw a ball, okay, in the air with some speed, how much time it will take it to come back to the ground? Now tell me, will you open the copy pen and solve the equation, or will you start throwing the ball outside? What will you do? What is the best option to do? Just do the calculations or just start throwing the ball? Tell me, very simple. This question was asked to me in the ISER Kolkata interview. Yeah.
Sir, question again, please.
You will do the calculations. So we should know how to calculate it. So observables are represented by the operators. So for each observable, there is one operator. So let's see some of the operators. If you want to measure the position, let's say X position, or let's be in general R vector, because we are interested in 3 dimension. So X, Y, Z, all 3 R vector. This is a physical quantity. Its operator is also represented, is also R vector. There is no change. Okay, there is no change. If you want to measure the kinetic energy, okay, its operator is T cap, which we describe it as minus iota, minus h cut square by 2m curly square by curly x square. Or if we talk in 3 dimensions, can you tell me how curly square by curly x square will transform?
Transform into del square.
Del square. Okay, so in 3D it will be del square. It's a very simple vector calculus. If we want to measure momentum, we say it is minus iota h cut curly by curly. Or if I talk in terms of vector 3D quantities, it will be gradient. Okay. So similarly, for each and every physical quantity, there is an operator. Okay, there is an operator. Now this is an operator. Operator, what does the operator word means itself? Operator word itself means that it has to operate on something. Okay, let's do the experimental versus theoretical physicist war. Okay, let's have a war between these two. So if you want to measure an energy, what you will do? You need some experimental device some experimental device, and what is the second thing that you need? What is the second thing you need if you want to measure energy of your system? One thing you need is an experimental device which can measure this energy. What is the second thing that you need? Any guess? Make a very quick guess.
The formula?
Something to measure the time.
Any quantity to measure?
No, you need system itself, na? You need sample, na? Whose energy you want to measure? Am I right? You need system itself and you need experimental device. What does theoretical physicist need? Experimental device is being changed to operator. Let's say O cap. It can be in a kinetic energy operator, momentum operator, position operator, anything. So experimental device has been changed to operator and the system has been changed to state. State in quantum mechanics is described by the wave function phi. Okay, so now we will discuss in detail what is O cap and what is phi. Okay, so experimental device has been converted into O cap, which is called operator, and system has been converted into your state phi. Okay, because it's very simple. If it is an hydrogen atom, which is n equals to 1, you don't know it is in n equals to 1, but it is in n equals to 1, and you measure its energy, it will come out to be minus 13.6 electron volts. So in a sort, you measured the energy of this state. You measured the energy of this state. Okay, so system converts into state in theoretical physics. Now, very simple question to ask is, in experimental it is okay. I can measure the energy of the system and it gives me energy. But now in theoretical physics, I don't know what is the state of the system. I do not know what is the state of the system beforehand. Then how do I apply the operator on it and without doing the experiment gives me? So how you do in classical mechanics? You have an equation called Newton's laws equation. In quantum mechanics, you have a very beautiful equation called Schrödinger equation. So Schrödinger equation is a equation which is this. Okay, which is this. This is time independent. We won't go into time dependent because it's not a lecture of Schrödinger equation. So this is an equation which you solve. We only need to know the basics. Can you tell me what is this? I just described it in the previous slide. What is this?
Energy operator.
Kinetic energy.
Kinetic energy operator. Okay, and it is operating on your
Wave function psi.
Psi. What is this?
Wave function. Wave function.
No.
State of function.
No, this V. What is this V?
Potential energy.
Potential energy operator. Okay. Since potential energy and potential energy operator are same, we usually say it is as a potential energy. So it's always a potential energy operator. Now, what is this E?
Energy, total energy.
Total. Very simple as that. Okay. So this will give you some sort of differential equation. It's a differential equation. No? It's some sort. This V is not some constant. This V will be something like this. Alpha x square or sometimes beta x or anything like that, e raised to power x, some function. It will be some function. So what does this potential tells you? Actually, what is the forces involved in your quantum system? And this kinetic energy operator keeps in mind that what are the energies due to the motion in your system. Okay, whenever you are imagining in terms of the in quantum mechanics, never think that kinetic energy actually means something is running. Potential energy something means that it is above the ground. Okay, so it's completely different. Kinetic energy and potential energy actually are the very wrong words in quantum mechanics also. Everything has been defined only to describe an analogy, but it's working good for us. So okay, E is a total energy, whatever total energy our system has. So it's some sort of differential equation which you can solve and find the your states in terms of your total energy. Because until unless you know your total energy, then it's not, you can only find your phi in terms of your E. In terms of E. Then we know phi in terms of E. Then tell me how we know E exactly. Because the problem still remains. Now we can't do measurement. Then how we find this E? Because if we don't know E, then how we know phi exactly? That this is a state and this is an energy. For example, let me give you an example of one dimensional potential. You know energy very well. This is an energy you know very well. All agree? And yes, correspondingly, you know state also.
A square, sir.
Yeah. Now, can you tell me how you actually came to know this energy in theoretically? Just recap the derivation. Yeah, Shraddha, you want to know? Tell me something or ask. Yeah. Anyone? How you know this energy?
Yeah.
You all are BSc. Yeah.
Yeah, didn't get this energy thing that you said about kinetic energy and potential energy and total energy. That analogy you were talking about.
I was saying that these are not actually the kinetic energy or potential energy which we used to think in classical mechanics. Here, kinetic energy and potential energy are simply potential energy are representing what are the forces involved in the system, and kinetic energy means all the energy which is due to the motion. So this is what an analogy is. Now I'm asking the question that how you know this energy? Until unless you know energy, you can't solve this differential equation and exactly know what are the states. You want to know the state.
Using operator, Hamiltonian operator.
Operator, I have used it. Nah. You have got this differential equation. You have operated this operator, kinetic energy operator on phi. You operated this V on phi. You have E phi. Okay. Now you have to solve this differential equation. Operator will only give you differential equation which you have to solve. How you find this energy? Very simple. Just recap the derivation of one dimensional potential.
Is it from the quantum number? Is it from the quantum number? By knowing the level of quantum number, that is which state are it?
So it's just you are just rephrasing the question. Instead of saying how to find energy, you are saying let's know how to find n. Instead of saying how to find energy, you are saying how to find n. That's just a rephrase of the problem.
Sir, I think while solving the Schrodinger equation, we have assumed certain constants, and finally when we solved the Schrodinger equation, and then this constant has the dimension of energy, therefore we thought that this might be the energy of the system.
No. So very simple answer is boundary conditions. सुना है कभी word?
Yes, sir.
You all heard this word while solving infinite potential well, boundary condition. So what do you say there? Phi is 0 at x equals to 0 and a. Is this what you use? Is this what you use? And from there you find kx equals to n pi. And k is you already know. K in terms of energy you know. K is under root 2 me by h cut. And from there you find energy. Does it has anything to do with Schrodinger equation? In this entire energy finding, did you use Schrodinger equation at all?
No.
So from where the information about energy came? It came from the boundary conditions. That is something very foundational in the quantum mechanics. Because of these boundary conditions, quantization comes into picture. All the quantum numbers comes into picture. Because of these boundary conditions, your kx can't take all the values. It has to take the values in the terms of n pi. So this is the first step where the quantization came. So whenever in the interview someone asks you in quantum mechanics from where quantization came, so always answer from the boundary conditions, because quantum mechanics has to obey some sort of boundary conditions. So we know the energy now. We can easily solve this differential equation and find out the states. So if it has energy En, it has state phi n. Now experimentally I told you state describes some physical quantity. Okay, but a theoretical physicists do not like this idea. Theoretical physicists say state is some mathematical equation. From this mathematical equation I can give you everything. So theoretical physicists find phi n, and from this phi n he can give you En, he can give you Vn, he can give you angular momentum, he can give you linear momentum, each and everything a theoretical physicist can give you if he finds this states. Just like in potential well we do find that. But in order to find that, we only need Schrödinger equation, and in order to know the En, in terms of which we need to find this equation, what we need is boundary conditions. So boundary condition plus Schrödinger equation solves the entire problem for you. Why I am spending so much time in giving you a idea about quantum mechanics? That's a reason, because you start thinking in terms of quantum mechanics, then it will be very easy when I will be doing matrix formulation and so on. So what will okay, so what we learned today so far? So what we learned today is that we have an operators, different operators. Every observable represents one operator, and we have a states phi. So phi we can know from the Schrödinger equation plus boundary conditions. Now let's see what are operators. How we actually know the operators, how we actually define the operators. Okay. I said that this is an operator for this is an operator for this. But I don't think so you have to go in that detail how the operator for linear momentum came. You don't have to go in that much detail in any course of quantum mechanics. You don't only have to take an idea that okay, this is how operator is. But now we have to complete the problem of theoretical versus experimental. This story needs to complete. And how this story will complete. Now this experimental device measured something on the system and gave you some value. Now where is that value? In your theoretical picture, where is that value? Is it in the equation, whatever is written so far? So number one thing, on which this operator will act on state. So let's complete the left hand side first. So operator is acting on a state. Now your state will remain there. It will still remain there. You are not destroying the state. But where is the value which you got? So that is written here. And this completes the story of a theoretical physicist. This is called eigenvalues. This is called eigenvectors, which you will hear a lot in quantum mechanics. And this is called operator. Have you seen such equation anywhere in mathematical physics?
Yes, sir. Eigenvalue equation.
Eigenvalue equation, very simple, very simple. Now, if I ask you, what is an eigenvector? Oh, I say this is an eigenvector, but eigenvector of what? Eigenvector of this
State.
Operator phi. No state. Eigenvector is a state, but it is a state of which? of this operator, of this operator. What do I mean by this? Very simple, very simple. Keep it very simple. Let's say you are measuring energy. Okay. Its operator is h cap, and you measured energy E1, which is an eigenvalue. Then you have a state phi1. Then this eigenstate is a state associated with energy. Means you have described these states with respect to E. For example, very simple. If you are measuring the acceleration of a system, okay. So if you come out to be your state is A1 and you measure the acceleration, let's say 2.8 meter per second square. So you say A1 is a state. Similarly, if you are measuring kinetic energy, you say T1 is your state. So with respect to this operator, these states are defined. But a very good feature in quantum mechanics is if you know the eigenstate for one operator, if you know the eigenstates for one operator, you may know the eigenstates for other operator also. So don't go in that detail. Don't go in that detail. Keep it very simple. We only want to understand how quantum mechanics works so that we can move on to 3D quantum mechanics. So state is described by phi, which is solved by Schrodinger equation plus boundary conditions. Any observables are represented by operator, and operator acts on state, gives you some value of that quantity and gives back to your state, gives you back your state. So this is called eigenvalue problem in the quantum mechanics. So I now quickly want to come and describe one thing which is very nice. Very nice. So spin of an electron. Now let's apply whatever we have learned today. So there is an electron, experimental person wants to do experiment. There is an electron. Okay. And there is some device which can measure this electron. Let's say Stern-Gerlach experiment. Stern-Gerlach experiment can measure the electron's spin. So according to you, what are the two states of this electron? One is up and one is down. Okay. One is up, one is down. These are the two states. What is an operator? Operator is S cap. What is this? Spin angular momentum operator. Spin angular momentum operator. Very simple. Or no. I think it is MS operator. Sorry. Okay, it is MS operator. MS operator. Do you all understand till here? This problem, spin of an electron problem. Do you all understood? Two state is spin up, spin down. Operator is MS cap. Do you all understand?
Yes, sir.
Okay, all understood. Now, if I measure this MS cap on this state up, what will you get? H cut by 2 and state back. All agree?
Yes, sir.
You must have heard this, or we can say this operator is SZ cap, so that we are close to the notation which is used in the book. That's why I'm saying it is SZ cap. So you all must have heard this thing, MS H cut. Have you heard this formula? These two formulas are very basic. These two formulas, have you heard? If not, we will discuss it in the third lecture. Okay, but very simple. So if I measure SZ cap on spin up, I will get H cut by 2. Why I'm getting H cut by 2? Because spin is plus minus half. But in order to have an angular momentum dimensions, h cut needs to be there, na? Because we just discussed that h cut has a dimensions of angular momentum. Now what will I get if I say, if I measure this?
Minus h cut.
Absolutely. Absolutely. So do you understand how the things are working up? Now let's do similar thing for hydrogen atom. Or let's do one more thing. Let's say now I measure spin operator on my state up. What will I get? One is state up, then other than that, what you will get? Just use this formula. Put s equals to half. You will get? How many of you agree?
Yes.
Yeah. Do you agree? Yeah. Anyone have any question? Yeah. Is it fine? All agree? Now tell me, if I do the same thing on this spin down, do you get the same answer or something else? I think my screen is frozen. Can you see the screen?
Yes, sir.
Okay.
Yes,
So if
sir.
I do the same thing, yeah, if I do the same thing on spin down, again, I will get the same answer. Here, I just want to discuss the difference between S and MS. Your electron has a spin half, always. S is always half. Your MS is plus and minus half. MS describes the direction. Okay, how it describes the direction again in lecture 3rd we will discuss. But S is a spin which is always half for electron, neutron, proton, always half. Either it is in space state up or it is in state down. So now tomorrow what I will do is we will actually study single states. It is in state up or state down. What if can in quantum mechanics is it possible that we are 60% in state up, 40% in state down, or 50% in state up and down? In classical mechanics it can't happen. If a person is running in one direction and another person has to run in another direction, it is not possible that person can run 60% in one direction and 60% in another direction. In classical mechanics it's not possible. Is it possible in quantum mechanics? If yes, then what are the values which our measurement quantities give? Let's say you are in a state which is 50% state up and 50% state down. Okay, 50% plus 50%. Okay. Now if I measure the angular momentum of this combined state, what is an answer which I will get? That's a big question. Number one. Second question which we will answer tomorrow is how mathematically we can how in matrix formulation we can represent state, operators and your eigenvalues. Because if this equation is true, this eigenvalue equation is true, what does it tell you about O cap? It can be a matrix. O cap can be a
Yes, sir.
matrix. Phi
Yes,
can
sir.
be a matrix. And other phi is also matrix. Since we have also studied this in matrix formulation, it means we can write operators in terms of matrix also, which is asked in the quantum mechanics competitive exams. All the competitive exams they say what will be the matrix for L vector, what will be the matrix for S vector, what will be the matrix for SZ, ladder operators, all things. So we will write the matrix operators and operators and their matrix representations. In 3D quantum mechanics, we usually discuss angular momentum and spin orbital and spin angular momentum and their matrix representations. So tomorrow we will write the matrix representations and their proper formulation. Today we discuss how quantum mechanics actually works. This nowhere is written at one place, so I will recommend, I will upload this video on YouTube again. Please go through that video, this video again, and think what has been told today. And as we will go along, you will actually have a understanding. From tomorrow, we will actually be in complete mode of competitive exams, how the question comes, how the formula works, and so on. But to understand that, it was required that there should be a one storyline of the quantum mechanics. So that has been discussed today. So most of my work has been done. Homework for you all is, if you really want to get a benefit out of this, please go through the derivation of infinite potential well. You should have a very solid grip over infinite potential well. I have taken lectures on that. You can go and watch on YouTube. They are also available in Telegram group. So please watch those lectures and read any good book, Griffith's kind of book, so that you exactly know what does infinite potential well means, how it is being solved, what is its energy formula, how it graphs, so on. Because in entire understanding of quantum mechanics, I will be using that. And that is a very basic that you should know. Okay. So with this, I think I will end the today's class. We will again meet tomorrow. And in 4 or 5 lectures, we will complete quantum mechanics in 3 dimensions, which will assure that there will be at least 3 to 4 marks is done in your exams. Okay. Okay. So any questions if you have?